Hey everyone. When we launched our Spacetime Patreon, we thought maybe we'd offset costs by a bit, but your support really blew us away, and you've allowed us to set our sights on bigger goals. We hit our $10,000 goal a few months ago, and as promised, we've made a Q&A video based on the questions you posted. So let's launch straight into them. Thomas Wilhawk asked, if dark energy is an inherent property of empty space, why can't we measure the force of expansion on less than galactic scales? Shouldn't the expansion force per cubic meter of empty space be the same everywhere? Hey Thomas, yeah, you're right in saying that dark energy should exist everywhere. However, its effect on scales that we can measure on Earth would be incredibly tiny. Also, it's not clear that dark energy would even have an anti-gravity effect in a lab on Earth. Dark energy exerts this effect because it has negative pressure in an expanding spacetime, and that's related to its constant density. Within a gravitational field, spacetime isn't expanding, so dark energy should act like regular energy. This is really one of the most intuitive things in all of astrophysics, so I'm really going to have to refer you to our dark energy playlist. Brandon Conroy asked, which field of physics is poised for the biggest breakthrough over the next couple of decades? Well, Brandon, I love any opportunity to make wild speculations that will almost certainly be wrong. I'm going to go with quantum computing, because it really seems like we're on the verge of actually making a true quantum computer, jumping from a few qubits to hundreds or thousands. Even if that's a generation away, which it may well be, the implications will be profound. Among other things, the physics breakthrough of quantum computing may rapidly accelerate the computing breakthrough of true artificial intelligence. That will change everything. Matt Roberts is curious which wacky or disproven theory in physics I would most like to be true. Well, obviously I'd like for pretty much every alien theory to be true. I really want there to be aliens. In reality, there's zero convincing evidence. Stupid evidence-based reasoning. The other one would be traversable wormholes and warp drives, which would let us travel faster than light. Both require the existence of negative energy matter, which doesn't seem to exist. Stupid light speed. Max Levine asked for the latest news on the TRAPPIST-1 system. What do scientists expect for the planet's atmospheres? Which is the best pick for habitability? So, the most interesting recent thing is a new, much more robust estimate of the star's age. Previous work suggested that the system was young, perhaps only 500 million years old. But last month, Burgasser and Mumijek published their estimate based on a few independent methods. They claim 7.6 billion years, which is older than our Sun. If this is true, it makes the planets of this system much better candidates for habitability. It also suggests that the planets are actually in stable orbits, which many people doubted due to their close proximity to the star. There's also been a bunch of work done on estimating the likelihood of liquid water and atmospheres on these planets. These M-dwarf stars emit a lot of UV light and have strong solar winds. While the TRAPPIST-1 system is on the low end of emission activity, it's estimated that only planets G and H could have retained oceans over the life of the system. Atmospheres themselves may have been ablated away by those solar activities, but the low density of the planets suggests lots of volatiles in the ground, which may have replenished those atmospheres. If any of the planets do have Earth-like atmospheric densities, then the James Webb Space Telescope should be able to see them. Patrick Gilmore asks if there's even a shred of evidence that Hawking radiation is real. The answer is nope. Nothing remotely convincing. The only thing we can point to is the absence of primordial black holes below a certain mass, which, if they once existed, may have evaporated away due to Hawking radiation by now. But we really have no idea if they once existed. Perhaps if we become very sure that primordial black holes of masses less than around that of the Moon should have been formed in great numbers in the early universe, that could be taken as evidence of Hawking radiation. But otherwise, we're a very, very long way from confirming it. Dan Brown asks whether all of the low-hanging fruit discoveries have been made, or whether there might be something obvious that we're still missing. Well, I suppose the unification of quantum mechanics and general relativity, for example, might be something stupid obvious that no one has seen, but I tend to doubt it. There are so many more people working in physics now compared to Newton's time that surely someone would have spotted it. On the other hand, I believe that the underlying explanation for, well, everything must be fundamentally simple, and that it will be very obviously the answer when we see it. But in order to see that fundamental truth, we may need to construct ways of thinking that are foreign to us now. To put it another way, the deepest understanding of the nature of reality may be a low-hanging fruit, but we're in the wrong garden. Daniel Brown, not to be mistaken with Dan Brown, asks whether it's possible to make a sustained singularity on Earth. For example, could the tiny singularities that the Large Hadron Collider is supposedly at risk of making somehow be made stable? Well, assuming that Hawking radiation is real, then the only way to stop a small black hole from evaporating is to feed it. That's tricky if the black hole is the mass of a particle, but something a bit larger, say the mass of a building, sure. Magnetically confined and consistently fed, and you have a pretty awesome power source. In fact, you get perfectly efficient conversion of mass into energy. Paul asks, I imagine PBS Spacetime is taking an incredible amount of your time, and it could grow if you let it. How do you balance this project with being a professor, which itself can take an incredible amount of time? Yeah, without question, the last couple of years have been the busiest of my life. I really love the real-life teaching, and I got into this whole science gig for the research, so I try to keep that up. Fortunately, there was a bunch of time I could free up by not having a social life and getting way behind on Game of Thrones. Richard Broman wonders if there could be black holes made of dark matter out there. So, a black hole made of dark matter would look just like any other black hole. And it's certain that any real black hole actually does have some dark matter in it. However, it's unlikely that dark matter could form a black hole all by itself. The stuff just doesn't seem to clump together enough to do so. Matt Gibbons asked whether quantum fluctuations are likely to be truly random and what that says about whether two identical universes evolve in identical ways. Well, that's a great question. Are quantum fluctuations random, or is there some underlying determinism that defines them perfectly? To ask this is to ask whether quantum mechanics in general is fundamentally probabilistic or deterministic. And I honestly don't know the answer. If it's deterministic, then yeah, two separate universes with exactly the same conditions at one point in time should evolve in perfect synchronicity. Stuart Milton wants to know where I'd place my bet on the solution to the Fermi paradox. In other words, where is the great filter that has apparently so far prevented the development of an observable advanced civilization? Well, based on the fact that we really aren't that far from making some sort of observable impact on our solar system, or even on the galaxy ourselves, say a few hundred years off, it's really hard to believe that the great filter is ahead of us. We may destroy ourselves before becoming observable, but I can't believe that essentially zero civilizations survive that couple hundred years of teething problems before they build some nice von Neumann probes or Dyson spheres or colonization arcs. For that reason, I think the great filters are behind us. Perhaps there's one very difficult transition that only very few, including ourselves, have crossed. Or perhaps it's a chain of improbable steps that we happen to get through a bit faster than most. The latter seems a bit more likely to me. Will Gehring would like to know the most recent science fiction book I've enjoyed. Well, my leisure reading time has taken a huge hit because of Spacetime, so the last really good sci-fi was Ready Player One. Right now I'm reading The Three-Body Problem because Grayson nagged me for months. I'll let you know when I'm done, but I expect good things because Grayson has never led me astray on nerd stuff. Richard Weisiger is rightly fascinated by the crazy amount of energy that is apparently dumped into gravitational waves when black holes merge. Yeah, well, such a crazy amount of energy tied up into something with such a minuscule effect on its surroundings. But in fact, energy stored in gravitational waves still adds to the mass energy of the universe. The universe doesn't get functionally lighter when a gravitational wave is created. Richard also asks how much mass is tied up in these waves across the universe. Well, I actually have no idea. I never thought about that before. But given that each black hole merger seems to release of order 5% of its mass in gravitational waves, it can't be a significant fraction of the mass of the universe. Black holes comprise something like 1/1000th of the baryonic mass of the universe, which itself is around 20% of the matter content of the universe. That makes the mass in gravitational waves something like 10 to the minus 5 of the total mass of the universe. Roman Odesky asks whether the space-time curvature affects the propagation of gravity and gravitational waves themselves. Well, absolutely it does. Think of the old rubber sheet analogy for space-time. If a heavy ball makes a depression in the rubber sheet, any wave propagating along that sheet has to follow the curve of the surface. Christian Gonzalez Capizzi asks what advice I'd give an aspiring undergrad physicist. Hey Christian, so you've chosen a challenging but incredibly rewarding path. Maybe you were the smartest kid in class in high school, but you won't be forever. And that's an awesome thing. If you're always the smartest in the room, then you're in the wrong room. So, to succeed, you're going to need to keep your sight on your dream, and that means remembering how amazing the universe is. When you're neck deep in electrodynamics or statistical mechanics, keep in mind that you're learning the source code of the cosmos. It was never going to be easy, but when you're done, you'll be able to speak fluent universe. David Lott would like a little screen time with each member of the Spacetime team. Sure, everyone meet everyone.
Hi, I'm Rusty. I am the producer of Spacetime. Some of the things I do are read the scripts and then say, Matt, I don't understand this at all.
Hey, I'm Kurt. I do the graphics for Spacetime. I make the lines and the spacey things move around and explode and stuff like that.
And I'm Mike. I'm the assistant editor, and I help out with sound effects and also editing things.
Hey, I'm Grayson. I was the graphic artist for Spacetime for about 1.5 years, and now I work on Spacetime VR with Kira.
Hi, I'm Kira, and I'm the developer for Spacetime VR.
Okay, that's it. There were a few questions that I didn't have time to get to, sorry about that. I'll try to answer them on the comment thread when I get a chance. Thank you for your brilliant questions, and thank you for believing in us enough to lend your support to Spacetime.